Alright, geometry, I have a bunch of stuff in front of me I could be doing for your video enjoyment between now and the test, and I want to be the most effective and efficient and quick about it as possible. Problem is, I'm out all day on Friday and Saturday doing workshops with the central office at SAS, and then Sunday is just the day before the test, so I will do a bunch on Sunday. Right now it's actually Thursday night, and I am going to do the following. These are the questions I got over I guess this would be the 12.4 homework from both classes that I haven't that I was asked, and this would be the stuff from 12.5. I'm going to kind of just bounce around because I want to get to everybody or every section and every concept kind of quickly. So I'll just kind of alternate between one of these and then one of these, and then when I get to the end of this video, I guess I'll be over here on your screen, I will do some from the super huge review packet, and I'll start with things that are, I think, going to be the stuff that people are going to make the most mistakes on, so that those are going to be out there here on Thursday. So you'll have access to those for the longer part of the weekend. And then as the weekend progresses, you might see more and more things up on the YouTube channel. So keep an eye that way. All right, so here we go. These are the ones that I had already done in class a little bit. And I'll put the page number on here, so as you scroll through YouTube, you can kind of see when's my question up, because I'm not going to go through these in order. Okay, so the first one is from page 511, and 511, this is the one that's on similarity, and this would be the one, this would be the page that's on spheres. Okay, I don't know if that's helpful or not, but anyway, page 511, this is actually both, because it's about similar spheres. But they ask you to do stuff in ratio. It's a very 12.5 concept. So we have two spheres. The radii are 6 and 10. They tell you that one of them weighs 4 kilos and ask, well, what's the other weight? These weights have to talk to each other in terms of k cubed. They have to talk to each other on the k cubed channel. Weight operates like volume. I guess I should say volume or weight. They talk about that in the book. Weight isn't technically a volume measurement, but its similarity ratio is in the same capacity as, and capacity is a good word for that actually, as volume. So I have to basically treat 4 as if it were a volume, like 4 cubic meters or something like that. And when I go to convert that, I have to use the cube of the ratio of sides. Ratio of sides is 10 to 6. The ratio of lengths, the one-dimensional ratio, I always do big over small. You could do the other way, but then you have to do the other step differently. It's up to you. I'm saying this one has 10/6 as big of length as this one, which reduces to 5/3. So k is 5/3. Everything in this, every length on here is 5/3 longer than this one. So every volume is 5/3 cubed times bigger. So that volume was 4. Now it's this thing, about 18.5. All right. The next one I did was also from that section, but this is page 512. It's a similar pyramid situation. They didn't even tell you it was a square pyramid. They tell you there's just two pyramids where there's a cut here. They don't tell you what the base shape is, and they don't really need to for what they're asking. They're saying the volume of the great big thing here. They do give you these numbers that I have in black. The volume of the great big thing is 250. What's the ratio of, oh geez, what is the question? What's the volume of the top? What's the volume of the bottom? Yeah, probably that's what it is. What's the volume of the top? What's the volume of the bottom? If this height is 9 and the difference here is kind of 6 between these planes, overall height is 15. Well, if I know the volume of the big thing is 250, I can find the ratio between that and something similar to it, which is this one up here, just the top piece. The big one has a ratio, has a height of 15. The top one has a height of 9. So it actually is a lot like those spheres we were just looking at. This one has a height of 15. This one has a height of 9. So the ratio in lengths from the big pyramid and the top pyramid is ironically also 5/3. So that means, yeah, any length on the big one is going to be 5/3 longer than any length on the small one, and that means any volume is going to be 5/3 cubed times any volume on the top one. Well, you know the big one first, so I have to divide by 5/3 cubed. Yeah, 250 divided by 5/3 cubed. I could have written that better like this: 250 divided by 5/3 cubed. That's like writing it this way: 250 times 3/5 cube. Invert and multiply, and I do that and I get 54. Then if I know this top volume is 54, I know the total volume is 250. It's just about subtraction to get the volume of the bottom thing there. All right, last one I did in class before I go to video live. Oh, you can't see that bottom thing. Can I move this down? Maybe. Yeah, okay. chopped off the top of that cone. 18 on 512. These are both on 512. We have similar cones. They tell you the volumes. Well, when they tell you the volumes, you know that that ratio, and again, I always do big to small. You could do small to big. I did 96 pi over 12 pi. That ratio is the cube ratio. That is k cubed. We need to compare areas here. I need to take this small area and convert it to another area. That's on the k squared channel. So I need to get from this k cubed to figure out what k squared is. The best way to do that is actually convert this into k. So I took k cubed and cube rooted it. 2 times 2 times 2 is 8, so that would be 2. K squared then is 2 squared, which is 4, and that means these areas are 4 times these areas. If the volume is 8 times bigger, the area is 4 times bigger. The lengths are double. If they ask me about circumference, I know this circumference is twice of this. The radius here is double here. The slant height here is double here. The surface area here is 4 times the surface area here. Okay, I'm rambling. Number 9 is a lot like the truncated pyramid we just saw on the previous page. I have a... Actually, let me read the question for a second. Yeah, they tell me these two heights. They tell me this is 9 and this part's 3. So I could separate these two things, and, well, not really separate, but redraw them separately. The top piece has a height of 9. The bottom, the entire cone, the great big cone, all the way to the floor, has a height of 12. So the length ratios between big and small here is this one is 4/3 times longer than this one. On A, they're asking about an area ratio. Well, the area ratio would be that thing squared. It's the ratio of length squared, which is 16/9. B is also about an area ratio. C and E are a little bit interesting. Let me get back to C and E. First of all, the next easier question I think is D, which is then what's the area of volumes between the big one and the little one? Well, it's area of length cubed, which turns out to be 67/24. Now for C, we're back on the area thing here. They're saying if this... is it lateral area in C? Yeah. The lateral area of the bottom part to the top part, or the top part to the bottom part. It's just between the sections. Top part to bottom part. Well, if this little area is 9/16 of the whole, then like this is 9 of the parts, and this would have to be 7 of those parts because there's 16 parts total if this is 9/16. So this is 9, this is the other 7. I just took 16 minus 9, got 7. Same thing with volume on this one. This volume is 64/27 of this, or you can think of this as 27/64 of that. The other 64ths are found in the bottom to make up this total 64/64. So if I subtract, I find out how many 64ths are in the volume of that. Kind of a silly way to ask that question, and you can tell by my tone of voice on C and E how much I like those. Hint, hint. Okay, now I'm finally ready to do something from this first page, page 500 and 501. I'll do the first one listed here, which is 20. And you know what, I'll just edit this. So you can see sort of, if you're watching the videos go by, you can see what's left in the video as you scroll through if you're looking for your particular problem. All right, this one is about the silo. It tells you, I changed this into this radius being 5. It says it takes 2 cans of paint to paint this top piece here. And then it's saying, well, then how many cans of paint should it take to paint the bottom part? The surface area of this little piece here is half of a sphere surface area, which is 4 pi r squared, divided by 2, because it's only half a sphere. A lot of people forgot to divide by 2 on the quiz when it's only half a sphere. That's 100 pi divided by 2, so this is 50 pi. If you're good with ratios, you can maybe do this in ratios and not even have to figure this out, but this is not that bad, so it's not too bad. The lateral area here is perimeter times the height, which is 2 pi r. R is not 2, R is 5, times 20, which is 200 pi. Well, if 50 pi takes 2 cans, how much, you can almost do this in your head, how much should 200 pi take? Well, it's 4 times as much as that was, so it's going to be 8. I mean, we got a little bit of similarity thing going on here. You could divide this by 2 and figure out that it takes 20, each can covers 25 pi. You could divide this by 25 pi, you're going to get 8. Either way. All right, 22, I think I did this in class, but I might as well do it here. It says you have a hemispherical bowl of radius 25. It says the depth of the water in this thing is 10. What is the area of the surface of the water? By the way, you can't, I really wanted to do this so much, but I kept thinking, oh wait, you can't do that. You don't have the tools to do that. I'm not sure I have the tools to do that. I can't ask you to find the volume of this water. That would have been kind of cool, but we aren't able to do that. Okay, so from here down is 10. I know from here sorry, from the bottom of the bottom of the thing all the way to the top must be 25. This is a radius of the sphere. If this part's 10, then this part here must be 15. The water is 15 from the top. I do that because I know this is a right angle here, and I can make a right triangle like this. And I can figure out, sorry, that's not the way I want to do that. I need to find this. This is the radius I need to know. If I'm going to find the area of this blue circle, I need to know the radius of it. Yeah. So I should have drawn the triangle this way. Yeah, I know this is 25. This is the thing that gets people. And this was all over the circle chapter. We had similar tricks. From the center to any point on the sphere is 25. So I knew it was 25 straight down. It's also 25 to this edge of the water here. This is 25. Can you see that? So I have a right triangle here. It's 15 and 25 in the hypotenuse. And I need, this is the thing I want to find, so I can get it now. This is the 3, 4, 5 triangle. Woo, pause for sneeze. Did you hear that? Did I pause it in time? That was really close. 3, 4, 5 triangle means this is not approximately equal to, this is exactly 20. And so it's just pi r squared at that point. And that's 400 pi. Love that problem. But again, we can't do volume, sadly. Alright, this one, I'm going to stick with 501 here for a second. I've already done more from 511, so to keep it fair. Alright, these things are supposed to have the same volume, and they have the same radius. The question is, what's the height? The volume of that thing is 4/3 pi r cubed. You could figure that out and then go to this thing and try to solve it, but I'm going to be fancy. I'm going to do this all at once. This is 1/3 pi r squared h. You know why I'm going to do that all at once? Because look at this. I'm trying to solve this for h, right? Divide both sides by pi. Multiply both sides by 3. Divide both sides by 8 squared. Actually that. And what do I have left? I have 4 times 8. The only thing left over here is 8. Is h. So guess what, kids? H is 32. I did not need my calculator for that. Okay, then the next question is prove that, or let's talk about surface area here for a second. And let's compare the area of the sphere to the lateral area of the cone. And it turns out that they're really close together, but they're not the same. The surface area of the sphere, area comparison, sphere and LA cone. They're supposed to be like 3% different or something like that. Sphere is 4 pi r squared. Now I can't put an equal sign here because they're not equal. This one is half. Does it bother you? I'm doing this like 2 at once. Times perimeter of the base. Notice I'm not stopping. You didn't tell me to stop. I can't hear you. 2 pi r times h, which I know now is 32. This is 64 times 4. Can't do in my head. Now here's a problem. I think it might have been the way they were doing their approximation for pi's or something, or their cube rootings or something. I don't know, their calculator problems. 8 times 32 is the same as 8 times 8 times 4. These are the same. What do you mean 3%? I'm guessing it's I don't know, a calculator error on their part, or approximation of pi kind of error. It's not 3% more. It's exactly the same. Interesting question. I'm glad someone asked that. Turns out they're not 3% different. They're exactly the same, and I've just proven it. Oh, wait. Warning, warning. Mr. Craig made a mistake. What is that? What am I supposed to put here? Glad I caught it. You would have gone through life thinking these things were the same. Laughed at math parties and ridiculed as an adult. Okay, this is supposed to be half. Maybe because I was doing 2 at the same time. See, it was my own fault. Half times p, which is fine, times L. What the L? That's not 32. That's the square root of, this is Pythagorean theorem, 8 squared plus 32 squared. There's where the 3% comes from. Alright, we need to figure out what this slant height is. Alright, so I go 8 squared plus 32 squared and take the square root of that. I know, I couldn't hear you. You were screaming at me the whole time, weren't you? I said, don't do it, Mr. Craig. Look what's behind that door. Alright, 32.984. Yeah, okay. Let's do that. 32.984. We're a little bit off. That's why they said calculator. Okay. Then I take that times 8 pi and see what we get. Actually, I want to take it times 8 first just to see. Times 8. So it's like 263 point blah, 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 pi. Okay. 263 point. How do you spell blah, blah, blah? You spell it 8787. Okay. Kind of looks like that, doesn't it? Pi, and this is approximated, and so I don't need to multiply those by pi to see that. Whoa, that's a 2. To see that it's so much percent, I just need to divide this by 256. Divide this by 256. It's supposed to be like 3% more. There you go. It's about 3% more. Okay, I feel better now.